Hello, my name is Scott Cheatham, and I'm a teacher with the Richmond Hospital Education Program. And today we're going to be doing a lesson on matrices. This lesson I've entitled Matrices Continued. I've created a matrix introduction lesson that if you haven't watched that one yet, I would suggest that you go over that first before you come to this one. If you have a basic familiarity with some of the ideas of matrices, you probably could start here. But this is going to assume that you have some basic understanding of what a matrix is and some of the basic operations that we can do with it. Matrices is a topic that first was originally in the Algebra 2 curriculum, although in the 2016 SOLs, they moved those out of Algebra 2 and into a couple other math classes. Depending on your teacher, they may cover this later on the year after the SOLs. But if you go on into trigonometry and some more advanced math classes or discrete math classes, this is a topic that definitely comes up. And really, a matrix is a way of organizing data. There are some helpful ways that we can use them. And it's a lot of the ways where computers actually store information, how they pull different pieces of data to do calculations on. Today we are going to reference a matrix calculator. If you've not looked at the Desmos matrix calculator, it's actually a calculator that they have created beyond their graphing calculator to do specific matrix operations. You can use a TI calculator. You can hit math and go to the matrix menu. I find that the Desmos calculator is a little bit more user intuitive and displays things nicely. But if you want to use your TI calculator, that is something you can do. Now to begin, I've got a few problems that I want to just go over to make sure we're all on the same page and just a little bit of review of some of the matrix basics. What I'm going to do is I'm going to put up these next three slides and kind of let you pause it on some notes paper, go ahead and answer them. And then we'll kind of talk over the answers together just to make sure we're all comfortable with the basics before we move into some of the more advanced things to do with matrices. So go ahead and pause this presentation and work on these three problems. All right, so for the answers here for problem 1, now this one is a problem where it's actually a word problem with matrices, and so you may or may not have seen one of these before. Again, as I mentioned, a matrix is a way of organizing data, and so this is a way of taking the information in a word problem and organizing it, and then being able to do some information from that. So go ahead and create these two matrices and see how you could solve this. Now, this is one example of how you could solve it. You might have done it a little bit differently, but what you do note here is if you did both P and N vertically, then it's going to not work that you can multiply them together. So when you're writing, if you have two different things that you're going to end up multiplying, so for instance, the number of points you get and the number of places that happened, you would have to do one of them horizontally and one of them vertically to make sure that the rows and columns matched up. And then you can multiply them together, get 56 points. We're going to go over how this would be calculated in just a little bit. This is the way you can multiply these two matrices together. Now this next problem gives you a little bit more kind of guidance on how to set it up to make sure that you can do some calculating. So go ahead and pause this presentation and take the information from this word problem and set up these matrices and answer these questions. And so the first two parts of this are just putting the information in a matrix in the form that, with the dimensions that they tell you. When you multiply them together, again, you would use a calculator there, and you would go ahead and multiply those together. Now it says what are the costs at store A versus the cost at store B, 48 and 76. And then obviously if you want which one you should buy from, should be store A, which is going to be the cheaper option there. This last one here, we're going to have two matrices. One of them is going to be about the fruit, the amounts of fruit, and the other one's going to be the cost. I'll go ahead and tell you the fruit is going to be a 3 by 3 matrix, and the cost is going to be a 3 by 1 matrix, and that way you can multiply them together. So again, the fruit, I want you to go ahead and make a 3 by 3 matrix, and the cost, I want you to go ahead and make a 3 by 1 matrix based on this information. And then you can multiply them together to get your total cost for each fruit and then the total cost for everything. So if you look at this, each column is one of the days. So you've got apples, bananas, and oranges on each of the days. Then you've got the cost, and then you would multiply those together. The total cost is going to be all three of them added together. Now, if those matrices were a little bit confusing for you to decide how you were going to set them up, that's why we want to go over how to multiply by hand. I think it can be a little bit complicated as to, okay, am I going to put these entries in rows or in columns? And so actually looking at where the math comes from multiplying by hand can help you understand where you should put certain items. So we're going to go over how to multiply these by hand, and it's a pretty straightforward process, but it can be a little bit tedious depending on the size of your matrices that you're multiplying. So the first question we have to ask ourselves is, well, can we multiply these together? And so we need to look at the dimensions there. Here I've got a 2 by 2 matrix and a 2 by 1 matrix. So again, looking at those inside dimensions, the columns of the first and the rows of the second, they do match. And then the outside numbers, that's going to be our new answer. And so we can multiply, and the outside numbers are going to be a 2 by 1, so we can get an answer when we multiply these. So we're going to have a 2 by 1 matrix, and the best way that I have always found to multiply these is actually to use your fingers. So what we're going to do is we are going to, for the first entry up at the top there, I want you to put your fingers on the 4 and the 5. And what we're going to do is you're going to multiply those numbers together, and we'll write this out. And then we're going to move our left hand kind of across the row and our right hand down the column. And so let me show you what that would look like. So for the first entry here, we've got 4 times 5 plus 7 times 1. For the bottom entry, we go down to, for the second row, again, the first column, 3 times 5 plus 2 times 1. And so when you talk about entries, you say what row it's on first and then what column it's on. And so you can kind of see how we choose which ones we are going to multiply. And then it's just basic multiplication and addition there to get our answer. 27 over 17. It takes some practice to get comfortable with what numbers you're multiplying and which ones are going to go in what spot. But again, the first matrix we're going to move left to right with the rows. The second matrix we're going to move up and down with the columns. And then we're going to add our entries there. So here are two matrices that I want you to give it a try doing it by hand. I'm going to show you where the numbers come from in just a minute. And this is going to be helpful the way so you get more comfortable setting up word problems, but also so that you can understand where we're going to build off of this with some inverses and other topics with matrices. So go ahead and pause this and give these two a try doing them by hand. Now for this first one here, again, asking yourself if we can multiply it. We've got a 2 by 2 and a 2 by 3. So those middle numbers and the dimensions match. We can do that. Our answer is going to be a 2 by 3 matrix. But again, so if I was doing this, I would start with my left hand on the 4 in the first matrix and my right finger on the 2 in the top, and then my left hand moves left and right. My right hand moves up and down. And so you get 4 times 2 plus 2 times 4. And then you can kind of see and look at this where the numbers come from, and then it's just adding them together. So if you need to pause here to kind of look at where those numbers are, I wanted to make sure I included them here. You can see where the answer comes from. Now in this one, the same process. We've got a 2 by 3 and a 3 by 2. Those threes do match, so we can multiply. And the outside numbers are going to give us an answer that's a 2 by 2 matrix. But for this one, when we multiply, you actually are going to add 3 different numbers. So for that first entry, we have 1 times 1 plus 2 times 3 plus 3 times 5. And so you just add all those up for each entry, and you can get your answer. Right, here are 2 special cases, and you'll kind of see why they're special cases when you start to multiply them. But I want you to go ahead and give these a try doing them by hand. And so we can see these special cases and that we're going to build off of kind of moving forward. So the first one there, that is what we call a 0 matrix. And that's where when you multiply these together, every entry is 0. So for that top one, you had 2 times 3 plus negative 3 times 2, and 2 times 6 plus negative 3 times 4, and so on. And it ended up that all of your entries were zeros, and we call that a 0 matrix. For this next one, this is going to be a little bit more useful for us, and one that we're going to use quite a bit is what's called an identity matrix. The identity matrix is going to have ones kind of down the diagonal and zeros in all other entries. This is something where an identity matrix is basically the equivalent of multiplying by 1 in real numbers. So we know that like a number 10 times 1 is 10. The identity property says that if we're multiplying, if we multiply by 1, it stays the same. For an identity matrix, that's what can we multiply where it will stay the same. It's going to be helpful for us to be able to calculate what is going to give us that identity matrix. And so that's a term that we want to be able to do. Now for this one, I want you to use the Desmos calculator. You're welcome to do it by hand if you want, but this one is if you look at it, it's a 3 by 2 times a 2 by 3, so we can multiply it, but our resulting answer is going to be a 3 by 3 matrix. So as we get into some of the more complicated and larger ones, it is going to be definitely fine and more time effective to use our Desmos calculator. And so I want you to make sure you feel comfortable doing that now. And here is your answer. And like I said, when you get into these larger matrices, it's going to be much easier to just use a calculator. Now, a new word that you may or may not have heard before is something called a determinant. A determinant is going to be something that we're going to use when doing certain calculations with inverses and identity matrices. But we first want to just kind of go over how we're going to calculate this number before we kind of see how we're going to use it. A determinant is going to be just a number. So it's not a matrix, it's actually a number. And we're only going to have determinants from square matrices. So if it's a 2 by 2, 3 by 3, 4 by 4, and so on. If you look at the Desmos matrix calculator, they use DET. Sometimes you might see D sub whatever letter the matrix is, or if you see kind of bars, it almost looks like absolute value bars around a matrix, that's going to be the determinant. We're going to go over, look at how you can solve it by hand for a 2 by 2, and then it gets a little more complicated if you go up to larger squares. So for the determinant of a matrix, or if you have those bars there, if what you look at, you have A times D minus C times B. Now, we are multiplying real numbers here, so the order that you multiply A times D, if you did D times A, doesn't really matter. But it is important that you do that first diagonal first, then subtracting the second one. This is something you'll be able to check using your calculator and get more comfortable doing. But note the change in the enclosure symbols there, and how when you're writing it out, if you see, rather than a matrix, like with the brackets going in, if you see those, what looks like absolute value bars, that's the determinant. And we're going to do A times D minus C times B. So go ahead and calculate this determinant by hand, and come back once you've got that. Again, we had A times D, so 7 times 3, minus B times C, or C times B, which is 2 times 2. 21 minus 4, and you get 17. Now I've left the work up here for these two. I want you to go ahead and calculate the determinants for these three. Hopefully get some comfort level with it. So go ahead, again, doing these by hand, calculating the determinant for each one of these matrices. And here you have your answers, -6, -19, and 28. Now, before we get into kind of how we're going to use these, I do want to just show you where the math comes for a 3 by 3. You're not going to be asked to do this by hand. It's a little bit more involved. If you ever get into a calculus class or even beyond that, you might need to do some of this by hand. So don't worry about doing a 3 by 3 by hand. I just want to show you some of the things, how it gets calculated. It's not the same as a 2 by 2 when we're doing these. We're going to, basically what you're going to do is you're going to cover up certain numbers and take the determinant like it was a 2 by 2 matrix. And then we're going to add, subtract, and add those three different determinants that we're going to get. So just want to show you this example and kind of where the math comes from. So if you start with 12, we're going to take the determinant of the bottom square, the 3, 2, 8, and 1. Then we're going to subtract, and we're going to have the 4, and we're going to take the determinant of the first column and the second column. And then you got this -1. We're going to take the determinant of the first column and the second column. And as I mentioned here, this is a very complicated process that really we're just going to use our calculator for. Because rather than taking three different determinants and remembering where you're at and subtract, It's a very involved process for 3x3 ones. So rather than worry about doing that by hand, I want you to go ahead and plug this next one into your calculator. So in the Desmos matrix calculator, go ahead and calculate this determinant by hand, or by using the calculator. And you'll see that you want to go ahead and define the matrix. And then all you have to do is hit determinant of A, and you can get your answer, which is 116. And just to show you the process for doing it by hand, you would have to set it up correctly, do 3 different determinants, and then combine all of those. And so for larger ones, 3x3s and above, we're just going to use the calculator. Just an important note, only square matrices have determinants. And so if you have a 2x3 or 3x5 matrix or whatever the case is, it's not going to have a determinant. And the way we're going to use this is actually in solving systems of equations that are typically going to have the same number of equations as they do variables. And so that's where this concept of a determinant gets used. But so as we move forward, we're only going to be able to calculate determinants for square matrices. Now, we showed you one of these before, but I want to show you how they're written out. So if you see I is going to, and then the dimensions there, I is going to be an identity matrix with 1s down the first diagonal and 0s in all the other entries. A 0 matrix is going to have 0, and then you notice here it's 2x2. It's going to be all 0s in all of the entries. Now we're going to start to look at this idea in this lesson of inverses, and then we're going to, in our next matrix lesson, we're going to use them a little bit more. But really an inverse is doing the opposite. And so for addition, the inverse of 5 is adding -5. For multiplication, which is what we're doing here, the inverse is going to be with real numbers, we think of it as the reciprocal. So 3 times 1/3. When we multiply those together, we get 1. And so that's something where the inverse in that case is the reciprocal. Well, in a matrix, we're going to follow the same idea, but it's going to be, okay, what can we multiply this first matrix by to get the identity matrix, which is what we consider 1. And so it's not going to be the reciprocal, it's going to be a little bit more involved, but we're going to have to use the determinant to be able to do it. So how are we going to determine what the inverse is? So this is where we need that determinant number. So what we need is we need the determinant. Now, this is a kind of formula and a process that you're going to get comfortable with, and it just takes some practice. We also will be able to use the calculator to determine these as well, but I do want to show you where the numbers are coming from. So in order to be able to take a 2x2 matrix and determine the inverse, and so again, that inverse is what can I multiply it by to where it's going to cancel out to 1. First, we need to find the determinant, and then we need to follow this formula here. So the inverse is going to be a scalar of 1 over the determinant times, and then you can kind of see what happened to the entries here. You flipped the A and the D, their location, and then the B and the C you kept where it is, but you negated them and made it negative. So let me show you kind of an example of what that would look like. So here we've got this matrix 2, 3, 4, 7. I'm going to walk you through this. So first we got to find the determinant, and then we got to use this inverse formula. So the determinant, again, that's 2 times 7 minus 4 times 3, and you end up getting 2. And then we're going to multiply that scalar of 1 over the determinant, or in this case 1/2, times how we've kind of flipped or negated those entries. And we end up with an inverse of 7/2, -3/2, -2 and 1. And this is a little bit more complicated of a process because as you've seen the way that matrix multiplication works, you're multiplying multiple entries in multiple rows and columns. And so this formula to be able to negate this is not as easy as just taking the reciprocal of each of the 4 entries. But what this would do, let me show you, we would expect that if you take matrix A and multiply by our new inverse, it's going to give us the identity matrix with those 1s down that diagonal. And so here we can check our answer. So we're going to expect that if we multiply matrix A times its inverse, we're going to get the identity matrix. So let's see what happens. So we've got our first original matrix A times the inverse. And again, doing that matrix multiplication by hand that we've been looking at, you can see that you end up with the identity matrix. All right, so I want you to try this one, calculating this inverse by hand. So go ahead and calculate that inverse using the formula down there on your own. And so we had our determinant of -1. Again, you flip the locations of the -3 and 2, and then you negate the -5 and 1, multiply that scalar through, and we have our inverse. Now for this one, something came up that was a little interesting when you were doing it. It's going to change what we have here. So the determinant was 0. This is a term called the singular matrix, which basically means there's nothing we can multiply this by that is going to give us the identity matrix. So it does not have an inverse. It's going to give you an error there. And so because the way we do that is 1 over the determinant, that's undefined. We can't multiply by that scalar. So it would not be a 0 matrix. There's no way of actually doing it. And so if there is no determinant, then there's not going to be an inverse. Now, as I mentioned, I do think it's important for you to kind of see where that comes from, and I'd like you to be able to determine that inverse by hand. But we can use our calculator to check or to oftentimes do this, and that's what we're going to do in our next lesson more so. So I do want you to plug in the inverse into the Desmos calculator here. Note that the inverse button after you put in the matrix is that A with the -1 up there and looks like it's in an exponent. So go ahead and plug this in now and calculate the inverse using that calculator. And so for here, you can see how you would just plug in A, do the inverse. Note that it doesn't give you the answer as a decimal. And so it is going to be oftentimes better to rewrite that as fractions. It's not wrong to leave it in decimal form, but we are going to, you might get some long, complicated ones. This calculator does not revert those back to fractions for you. It's something where you're going to have to kind of do that on your own. So that's something to just keep in mind. Well, we're going to pause there for this lesson. We've done quite a bit here working with determinants and multiplying matrices by hand. As we keep going with this, we're going to look how we can use these matrices to solve more complicated systems of equations and many of their other applications. But we want you to get comfortable with doing some of these multiplying and inverse operations first. I would suggest if you're with the Richmond Hospital Education Program, we have an IXL subscription and we can set you up with some more practice. It's still in Algebra 2 on IXL under matrices. They have quite a few different options, and I would say to practice some by hand, but you can do most of them using the calculator because that's what we're going to do moving forward. But we want you to be able to see where those come from because that's going to be important knowledge and how you're going to set up some of these systems of equations or word problems. And so you want to understand how the multiplying matrices by hand kind of works and why you would want to have certain numbers in rows and certain numbers in columns. But I thank you for listening. I hope it's been helpful for you, and I wish you well with the rest of your school year.